Hello and welcome to the next video on writing your own operating system. In this tutorial we will look at the Peripheral Component Interconnect, or PCI for short. Well, the thing is, before we had drivers for the mouse and for keyboard, and they were relatively simple because, I mean, a keyboard is a keyboard. You know, it's basically the same thing no matter which keyboard you have. I mean, there are exceptions, but it's quite standardized, and pretty much every computer has one. So it made sense to have something like a fixed interrupt for the keyboard and a fixed port for the keyboard. But if you take just some specific network chip, for example, not every computer is going to have exactly that keyboard, exactly that network chip, or a compatible one, right? So, and maybe you might even have multiple network cards with the same network chip. So then you would get some really big trouble if you tried to do this like we did it with keyboard and the mouse, because then you could only access one of them at a time. So what people came up with is the Peripheral Component Interconnect, the PCI, and that is really some, I think, some really well-designed hardware. So you have your processor, your programmable interrupt controller, and your PCI controller. And connected to your PCI controller are, for example, your graphics card, and your network card. Okay. And as I've said, it doesn't really make sense to have a hard-coded interrupt and a hard-coded port for these things, because you don't know, are they even there? Are there multiple of the same or multiple different? You know, there are just too many different scenarios. So what they came up with, and I think this is really a good design, is you can talk to the PCI controller and ask it, well, what device is on port number this? What device is on port number that? And what is the interrupt it's going to send to me? And so this really solves a big problem, you know, because before we had the situation. We would have hard-coded addresses, hard-coded interrupts and everything. And this was really a problem because there are just too many different devices, and you can connect them to your computer by putting them in different slots. You know, all the stuff, you know, you just don't know exactly the layout of the computer that your kernel is running on. So this really is a very well thought out way to configure your kernel automatically. So you don't have the user doesn't have to tell you the interrupts for the different devices. Okay. So and he doesn't usually have to tell you which driver to use for which device. Let's talk about PCI. So you can ask the PCI controller. A PCI controller has multiple buses, and So the PCI controller has up to 8 buses. And it's not even exactly, there's some debate what bus even means. Most people translate it with binary unit system, but whatever. I think it's not correct, but whatever. So you have up to 8 buses. Okay. And then on every bus you can have up to 32 different devices. A device can have multiple so-called functions. Okay, a function is, for example, your sound card. If you look into your hardware setup, you'll often find the sound card multiple times. Once as an audio capture device and once as a sound card. So devices can have so-called functions, up to 8 again. Okay, so to put this together, we have 8 ports, 32 devices each, and 8 functions each. So you will need 3 bits to encode the function, 3 bits to encode the bus, and 5 bits to encode the device number. Okay. Okay, so I would say let's start with the enumeration of these devices. So we will talk to the PCI controller and ask it, well, what is device number 3 on bus 1, for example? Okay, and then it will give us basically 2 16-bit integers. So uint 16t for the vendor ID, and a uint 16t for the device ID. So every major vendor has its own unique vendor ID, and okay, there can be at most 65,536 different vendors having such a vendor ID. I think smaller vendors share IDs, but this is really a very useful information when you want to decide which driver you want to instantiate to talk to a certain device. Okay, and every vendor can have up to 65,536 different devices. Okay, I think there are even vendors who have multiple vendor IDs, but whatever. The PCI controller will also tell you a more general information, something called a class ID and a subclass ID. So, and these are also 16-bit integers. And these are really useful for some compatibility modes. If you have For example, there's the class ID for multimedia devices, and then you have a subclass ID for VGA compatible, video graphics array compatible graphics cards, and then you don't actually need to look at the vendor and device ID, because if you just want to use VGA graphics, then this is sufficient for you, and then you don't have to write drivers for each individual graphics card that there is. Okay, so but of course, if you want to do something like hardware accelerated 3D graphics, then you really need specific drivers for the graphics card. But what we will do in the over the next videos is we will really have a driver for VGA compatible graphics cards, and to decide that we just need to look at the class ID and the subclass ID. Okay, so these are information that we will get from the PCI, and then based on that we can load a driver and put it into our driver array, and then then we can start drawing stuff. Okay, and that will be a big step, I think. So and actually, I think once you have the PCI driver ready, I think that's a very big step, because when you have that, then you have basically everything you need to really do whatever you want. So then once you have the PCI, you just need to look, what are my devices, and you just write your drivers for your devices and maybe some protocols implementation, like Ethernet 2, IPv4, TCP, and then you can communicate with networks and stuff. But the PCI is really a major step here. So once we have that, we are basically at a point where we can really start doing what we want. We just need to write the different drivers for the devices, but we have everything to connect these drivers together and load them. So yeah. Okay, so let's start with this. So in the hardware communication, I will create a new file, PCI.h. and PCI.cpp. Okay, so the PCI controller has, relatively standard a data port and a command port. In this case, they are 32-bit ports. Okay, and then, of course, one of the first things we want to do is we want to read data and write data. And we will just have a way of passing the ID for the bus, the device, and the function along with the read and write command. So we will have something like uint32t. Read method, which gets a bus number. A device number. And a function number. And also, so we will be able to read data from a certain function, okay? And the thing is, they all have some memory locations. They have some memory, and they have a standardized memory space. And so we will just have to read certain offsets of that memory, where we will find the class ID, the subclass ID, vendor ID, device ID, and so on. So what we have to also pass is the offset of the data that we want to read. You know, there's an offset for the class ID, an offset for the subclass ID, and so on. So we also have to pass the offset that we want to read. And then we'll have a write function, which also gets a bus device number function, register offset, and also another 32-bit number for the value that we want to write. Okay. So in the constructor, we will set the port number for the data port and the command port. So the data port is 0xCFC for the PCI controller. And the command port is number 0xCF8. Okay. Okay, so from these three numbers, we will construct from these numbers we will construct an identifier that we will send to the PCI controller. So the bus number is going to be shifted by 16 bits. The device number will be shifted by 11 bits. Will be shifted by 8 bits. Then the register offset isn't shifted at all. the first bit needs to be set explicitly to 1. So. Okay, and we will need to do this both in the read and also in the write method. And then we will write this number to the command port. And after we've done that, we can read the result from the data port. One thing you may have noticed, the register offset here. We take the bitwise AND with the number 0xFC, and that means we are cutting off the last 2 bits of this number. So this needs to, So this is actually. So the numbers are 4 byte aligned. So this is actually an address of a byte, but since the bytes are grouped as 32-bit integers, we ask for a location of an integer. Okay, so we cannot ask to get the second or third byte from that integer. We just get the full integer back. Okay. So I think I didn't explain that. I think I didn't explain that too well. Okay. So. So here's the data in the device, and maybe here is 4, here is 8, and so on. Then when you want to have this byte, you will have to send the number 4 so that you get this full 32-bit integer. And then you just have to extract this byte out of the result. Okay? So you can only ask for a 32-bit integer. So you can ask for number 4, you can ask for number 8, but not for number 6. If you want number 6, you have to ask for number 4, and then just discard the bytes that you didn't want. So then we will do this. Okay. And down here. We basically do the same thing. We've constructed this identifier that we want to have, and then we write that to the command port, but then we don't read from the data port, we write to the data port. Okay, one very interesting question is when we enumerate these all these functions. I mean, if there is no device on a certain bus, or maybe the device doesn't have multiple functions, then it just, doesn't really make sense to ask for each function individually. So because this would make the selection of the drivers quite slow. So we will need a way to ask a device if it has functions or not. Okay? And that's a quite simple question. So I'll just implement this. So bus number, device number. And since we have the read and the write already, this is quite simple then. So to find this out, we just need to read the bit with the address 0x0e. Function 0, the address 0x0e, but we only need the 7th bit of that. Okay, so we read this address, and the 7th bit of that tells us if the device has functions or not. And this will speed up the enumeration of all the devices and the driver selection by a factor of 8. Okay. So what we want to do in the end is we want to give the driver manager to the PCI controller and have the PCI controller talk to the driver manager and insert the drivers for the devices on the which are connected to the PCI controller. Okay, so we will want to have something like wait, we don't have drivers yet. Okay. So we want to have a method select drivers, which will enumerate the buses, the devices, and the functions, and select the drivers based on the information about class ID, subclass ID, vendor ID, device ID, and it's supposed to put these drivers into the driver manager on its own. Okay, yeah, and this will look relatively clear for now, so we'll just iterate over the buses, have a nested loop iterating the devices, have another nested loop iterating the functions. So. Okay, and the number of functions that we have to check will either be 0 or, I mean, a device has at least one function, so the number of functions is either 8 or 1, depending on the result of this device has function method. Okay, I think it's a good idea, although it will be a little bit more to write if we add another class here. Just to store all the data that we get, you know, the class ID, the subclass ID, all the stuff. And then we will have another method which we will call inside the loop, and that will give us an instance of this new class. So a number for the port that we will use for the communication. You know, this is the number that we will get from the PCI controller. One for the interrupt number. So here we will store the bus, device, and function. Vendor ID, device ID. Class ID is an 8-bit integer. Sorry, I was wrong on the whiteboard. Okay. Okay, so I'll add another method, which will give us such a descriptor. For a given bus, device, and function. Okay, these are just copied over. I mean, you could pass them to a constructor for the Peripheral Component Interconnect device descriptor object, but whatever. So So the vendor ID is on the offset 00. The device ID is on offset 0x02. The class ID is on 0x0b. Subclass ID is on 0x0a. Okay. Okay, so then in this loop we can just call this method here. Okay, like this. Now, the vendor ID will be either 0 or all ones if there is no device on that function. Okay, so if the vendor ID is either 0 or it's all ones, then we can break the loop, because then there are no more functions coming after that. Okay, I will, just for demonstration purposes, I will put 2 printfs here. Okay, so yeah, I'll just wait. Okay, so now I've included it in the project, and I want it to be known in the kernel and used in the kernel, of course. Okay, so let's see. Okay, so this is really an interesting output that we have now. So this really lists the devices that we have on our PCI controller. I think we should come to an end now. I think this video is quite long already. I think the point that we have reached now is also a good point to make a cut and continue in the next video. So the information that you see here is really, really good information that we have now. For example, you see here this vendor 1022 device 2000. This is the advanced micro devices, you know, AMD, the manufacturer, which also makes CPUs. They're quite commonly known for their CPUs. This device with the number hexadecimal 2000, that is the network card installed in this virtual machine. You know, it's the network card with the network chip called AM79C. I'll write it down. So 1022. So this is the AMD network chip for AM79C973. So if you write a driver for this chip, and you will find quite decent documentation about this chip online, then you will be able to send data over the network. You know, there's a quite good tutorial on that on lowlevel.eu, I mean, okay, we right now we have only found an interrupt, but we haven't found the memory location that we will use to talk to this chip through memory mapping. This is something we will do in the next video. But the thing that I want to tell you is these vendor IDs and device IDs are super interesting, super relevant data. So if you ever have any trouble with a PCI device, you just look at this vendor ID and device ID and you Google for this binary number, this hexadecimal number, and you will find forums where exactly your problem is discussed in no time and discussed by really competent people. So this is really a very, very useful information to for troubleshooting. And the data that you see here is actually the thing that you get if you use the Linux command lspci. You see here you have this information. It tells you what the devices are. You will find quite extensive lists on the internet, which vendor ID device ID combination is which device stands for which device by which vendor, you know. So as I said, this information here is very useful when you are troubleshooting stuff, and the output that you have here by LSPCI is basically the same output that you get from this list that we've just written. And you can do also LS-USB, which gives you another very similar list, but not for PCI devices, but for USB devices. And as I've said, this is really, really useful information when you have any trouble with your hardware. And when you go on forums on the internet where people discuss hardware problems, the people who help them will usually ask them to send the output of LSPCI or LSUSB as one of the first things they ask for. And now you really know why and what that does and so on. So yeah, that should be enough for today. Yeah. So we have a lot of communication with the PCI and the devices right now, and yeah, in the next video we will talk about the base address registers of the PCI devices. They will really tell you which memory location the device wants to use for memory mapped input and output. And once you have that, you can really communicate with the hardware and send your commands, and then you can write the drivers for the devices and have them have the instantiation put the instantiation here in this loop. So then you will have a really large, a really big leap for what your operating system can do. Okay, so yeah, tune in next time. Don't forget to subscribe so that you don't miss the next video. And see you next time.